here is topic 315, rates of change in polar functions. Okay, so in this section we will learn ways that we can describe characteristics of the graph of a polar function. Given the polar function r equals f of theta, we know that r represents the signed radius. We use the phrase signed radius because r can be positive or negative value. But remember, the radius is a length, so it can technically only be positive. That's why we call it a signed radius. As we trace the graph of a polar function, we are interested in whether the graph of r equals f theta is getting closer to the origin or farther from the origin over a given interval. All right, so this is a limacon with an inner loop, and we're looking at the changes in the distance from r equals f of theta to the origin. And the origin is the pole, okay? That's your 0, 0, basically. And so the distance between r equals f of theta and the origin is increasing when r equals f of theta is positive and increasing, or negative and decreasing. And the distance between r equals f of theta and the origin is decreasing when r equals f of theta is positive and decreasing, or negative and increasing. Now, I'm going to show you how to do all this with your rectangular graphs. Okay, but we're first going to look at this function right here as it gets graphed. Okay, so here's this. Now, as I start, okay, let me just draw it real quick. So remember that the blue circle, that is your that's just showing you how much of the unit circle that we are using. Okay, so the black part is actually the graph. So as my x values, my inputs, my theta values, go from 0 to, let's just go to pi thirds and stop. Okay, so if you look over here, you can see that the r value, so this is the distance from here to here, that distance is increasing. And I know that the radius is positive because my angles are from 0 to pi thirds, and the radius is in the first quadrant. Okay, so right now, the distance of the radius, the distance from the origin is increasing. Okay, then when it's increasing all the way to here. Now, once we get to pi halves, the distance from the function to the origin is decreasing because my r values are getting smaller. Okay, and so the function is positive and decreasing at this point. Now, once I get here, it's still decreasing. Okay, so now I'm at 0. So now watch what happens, because my angles are in the third quadrant, but my graph is going to move into the first quadrant because that means that my radius is negative. That means at this angle, I have a negative radius. That's why I'm plotting over there. So now my graph is getting farther away from the origin again, and then it's getting closer to the origin again, then it's getting farther away again. Okay, so now watch what happens over on the right-hand side, on the rectangular graph. When I'm trying to look at the distance from my function to the origin, I'm looking over here at the distance from the function to the x-axis. So look over here. My distance from my function to the x-axis is increasing, so we get to here. Just like the radius was getting, this function was getting farther away from the origin. But now, my distance from the function on the rectangular side over here, the distance from that in the x-axis is decreasing, just like it's getting the distance from the function to the pole on the left-hand side is decreasing. Okay, so then right here, this is where I'm at 0. Then I'm going to get farther away again. And then I'm going to get closer again, and then I'm getting farther away again. So the way I look at it over here, because what's going to happen over here is you are not necessarily well-versed enough in the polar functions to know where does this start getting graphed, right? But here, I'm starting at 0 and going to 2 pi, and I can tell you, just by looking at this, that from here to here, my distance from the graph to the x-axis is getting bigger. That distance is increasing. Then that distance is decreasing. Now that distance is increasing again because I'm going away from it. Sorry, I'm afraid I can't point and move this. and then my distance is decreasing again because I'm going back towards it. So if you can make sense of this graph with this, that's going to help out greatly. So let's go back over here and look at this. So this function, it is this same function here. So this is what we just looked at, and then this is the rectangular version of it. So we're going to get the intervals where the f of x is positive and increasing. I can just look at, we know how to find that on here. Positive and increasing. Positive and increasing is right here. I'm going from 0 to pi halves. 0 to pi halves. Positive and decreasing. Oh, wait, let me erase that. I skipped one. Here, positive and increasing there as well. All right, so I've got to go from 0, I've got to write a little smaller, 0 to pi halves, and 11 pi 6 to 2 pi. All right, that is positive and increasing. Now, positive and decreasing, this is positive and decreasing. So from pi halves to 7 pi 6. All right, negative and increasing is right there from 3 pi halves to 11 pi 6. And then negative and decreasing would be right there. That is 7 pi 6 to 3 pi halves. Okay. So what I was saying on the other graph, when I want to know, when we are looking for the distance between r equals f of theta and the origin, think of this curve as r equals f of theta and this line as the origin. So here we are getting farther away from there, then we're getting closer, then we're getting farther away again, then we're getting closer, then we're getting farther away. Okay? So this says, in the polar coordinate system, the graph of this function becomes this graph as shown in the table. The labeled points A, B, C, and D correspond to the intervals from example 1. Okay, so here we're looking at this compared to this up here, the A, B, C, and D. Because for A, from A to B, we're going from 0 to pi halves. Okay, that's what we wrote. From 0 to pi halves, that's how we're starting there. Boom. Okay, now that R value is getting farther away from the origin. Then from B to C, we're getting closer to the origin. Then from C to D, which is negative and increasing, I'm getting farther away again, then closer again, then farther away again. Okay, now they can give me these all day long. If I can sketch this in a rectangular coordinate system, I'm golden, because we can make sense of that stuff for sure. So let's see how that's going to work. All right, so it says, tip. It is often helpful to sketch the graph of a given function in the rectangular coordinate system. 100% think that's true. Okay, so this is what we want to graph. Okay, does it have to be beautiful, perfect? Absolutely not. So this is a cosine graph. That 2 right there means that, maybe I should make this a little bit better. Okay, so this 2 right here, that is my vertical shift. So if I go up 2, that is where my midline is. This is my A value, so I go 1, 2, 3, 4. I probably still should have done that better. 1, 2, 3, 4, but it's going to be good enough. Just watch. Well, it's going to be good enough, but let me redo it for y'all. You don't have to redo yours necessarily, but I guess I should have a semi-decent one. I just wasn't prepared for how much space I needed. So let me just move it down here more. Oh my goodness. All right. And remember, if you have to erase stuff on the AP exam, don't take the time to erase, just mark it out. All right, so let me do that again. Here is my midline. This is my A value, so from there I got to go up 4. And from here I got to go down 4. 1, 2, 3, 4. Okay. And this is a cosine function, so I know that my parent function for cosine looks like this, all right? Which means that I'm going to go, since this is negative, I start down instead of up. From the midline, I go down 1, 2, 3, 4. And then when I end, that's where I end. And then I know halfway between the two, I go up 4. So I'm right there. And then those two are halfway here, so I'm here and here. Okay? So you can sketch in the curve if you want, but you really don't necessarily need to. I mean, the curve is going to look something like this, right? But I've got my key points there, and that's all that really, really matters. And then I can figure out what my period is. My period for cosine is 2 pi. This b is 1, so that means this is at 2 pi. Which I can't really write. This is at 2 pi. So this point is at pi. This obviously is 0. This is pi halves. And this is 3 pi halves. Okay. So let's see what this says. It says, consider the graph of the polar function, Which of the following statements is true about the distance between the point with polar coordinates f, theta, theta to the origin? Okay, so from pi to, the distance is increasing for pi to 5 pi thirds. So if I start at pi, which is right here, and I'm heading to 5 pi thirds, like this way, my distance to the, quote, origin, which is, you know, if I graphed the, it doesn't even matter what this looks like when it's graphed. And if you don't know, that's okay. Because I'm headed towards this line here. So that is not going away from, the distance is not increasing, the distance is decreasing, so I don't like A. If I'm going from 5 pi thirds to 2 pi, okay, so 5 pi thirds is somewhere in here. It says the distance is increasing because f of theta is negative and increasing on that interval. All right, well, if I go from, I'm not even sure where 5 pi thirds is here exactly, but it's somewhere between 3 pi halves and 2 pi. And so I can tell you, but from all of that this function is not increasing at all. And this says negative and increasing, and maybe it's negative, maybe it's negative and positive, I don't care, but it's definitely not increasing, so I don't like B. Then it says the distance is decreasing for pi to 5 pi thirds because f of theta is positive and decreasing. Okay, so positive from pi to 5 pi thirds, it is positive and decreasing. Good with that. Then it says the distance is decreasing because it is, f of theta is negative and decreasing on that interval. All right, well, I'm not sure where if 5 pi thirds is a 0 or not, so maybe we could figure that out. Actually, it doesn't even matter. It is the 0, but it says the distance is decreasing. I read that wrong. So if, whatever it is, when I'm getting to 2 pi, the distance is not decreasing. The distance from this to this is increasing, so it can't be B. So my answer has to be C. Sorry, for a second there, I thought I liked 2 answers. All right. Now, if you're into this already and you've gotten this far, and I need to re-explain that to you and you need to ask me questions in person, please do that, because I think you can figure this out. If you cared enough to watch this video, I can help you get this figured out. Okay. So then we have the graph of f of x. Oh, I was going to show you. Let me see if this will actually work for me. So this is what we just did here. And so we can see that, let's just look at our answer choices. It said from pi to 5 pi thirds. That was the first one. So let me get to pi. So here's pi, okay? So from pi to 5 pi thirds, which is over here, that distance is decreasing, okay? So from pi to 5 pi thirds, the distance from the function to the origin from here to here is decreasing. And you can also see over here, this distance is decreasing. Let's see, from 5 pi thirds, which is like right here, to 2 pi, that distance is increasing. which is our answer choice B, that the distance from the function to the origin is increasing, but this says because the function is negative and increasing. The function is negative and it's decreasing. Okay, so I just kind of want you to see how these work together, if that helps you. All right, now let's look at example 3. I have 3 sine of 2x shown above in the regular coordinate system. If the polar function r equals f of theta is graphed in the polar coordinate system for 0 to 3 pi halves, and it's graphed for me, boom, boom. Which of the following intervals is the distance between the point with polar coordinates, so basically my polar graph, and the origin decreasing? So the distance from that, and I don't have the polar graph, and I don't care. What that is asking me is on what interval is the distance from this function that I see to this line, when is that, what are we trying to do, decreasing. Okay, so we start with 0 to pi fourths. Well, 0 to pi fourths, the distance from the function to this is increasing, so I don't like that. Pi halves to 3 pi fourths. The distance from the function to here is increasing, not what I want. 3 pi fourths to pi, that distance is definitely decreasing because I'm getting close to where I'm actually going to touch it. So I like C. Let's read D. From pi to 5 pi fourths, again, that distance is increasing. Don't like D. My answer is C. And then here is that graph. Let me make sure it's the right one. 3 sine of 2x, yes. So on the right, this is what they had graphed for us, but it's actually a 4-petal rose that gets plotted. You can just want to see what was what there. But you didn't have to know that to do that question. All right, so relative extrema, looking for max and min. You do not have to overthink this. You do not have to think about, you don't have to know what that looks like when it's graphed in the polar coordinate. Nothing. All you have to do is understand this and the rectangular coordinate system. Okay, so let's plot this. If I go, this is my vertical shift, so at 1 is where my midline is. My A is 2, so I'd have to go up 2 from there and go down 2. All right, and so sine, I know what sine looks like. That's a negative sign, but I know I start here, and I end here, and the middle is there. And then halfway between the two, I would go, supposed to go up 2, but this is negative, so halfway between the two, I'm going to go down 2 to there. And halfway between these two, I go up 2, and that's basically what it looks like. Then I can set my, my period. So this is 2, which means I take 2 pi and divide it by 2, which makes this pi halves, makes this pi fourths, and this 3 pi fourths. I'm thinking those would probably help me. And again, you can sketch in the sine curve if you want to, like connect the dots, but I'm going to maybe connect them as I go if I need to. But look what this says. This says, consider the graph of the polar function in the polar coordinate plane. Which of the following statements is true about the graph of r equals f of theta? This says the graph of r equals f of theta has a relative minimum on the interval from pi thirds to 2 pi thirds. Okay, so pi thirds is right here. It's between pi fourths and pi halves, and 2 pi thirds is right here. We do not have a relative minimum because that would be our minimum. I don't like A. We have a relative minimum on 2 pi thirds to pi. Well, again, 2 pi thirds to pi is over here. This is my minimum, so that's a no. The graph has a relative maximum on the interval from pi thirds to 2 pi thirds. So pi thirds to 2 pi thirds. This is my maximum, so that's a no. Then it says it has a relative maximum from 2 pi thirds to pi. Yep, there's my maximum. The answer is D. So you really do have enough information. You don't have to overthink it and get lost in all the polar stuff. But you have to be able to sketch these graphs. That's the thing. And again, if you wanted to actually sketch it in, I mean, this is what it looks like. But you don't even have to do that much. Just get those key points there, and you are good to go. All right. average rate of change. Oh, I was going to show you that one, I guess. Let me see if I have that. Did I do that one? Is that this one? 1 minus, yeah. Is that the one we just did? 1 minus 2 sine, yeah. So this is one that we hadn't actually looked at, but you can see it says, so here's what we were looking for, relative max and min. Your relative minimum from pi thirds. So pi thirds is right here to 2 pi thirds. Oh, sorry, pi thirds is like right here. Pi thirds to 2 pi thirds definitely doesn't have a relative minimum there because it's getting bigger. Here's what you can tell. Like, this is the farthest I get out, right? And that's positive, and that's my maximum. That's a minimum because it's a negative radius. And then that's another maximum. So here, my maximum on my rectangular graph is my maximum on my polar graph. My minimum on my rectangular graph is my minimum on my polar graph. And the reason it's a minimum is because that is a negative radius there. And then that's just a cool looking graph. All right, average rates of change. So in previous units, we learned about the average rate of change of a function in rectangular coordinates. In the polar coordinate system, we will find the average rate of change of r with respect to theta. It's still just slope, and it's still just f of b minus f of a over b minus a. No big deal, okay? So if I want to find the average rate of change, which just means slope, average rate of change for this on this interval, that's going to be f of pi minus f of pi halves over pi minus pi halves. Okay, so what do I need for that? I need f of pi and f of pi halves. Let me find f of pi. That's going to give me 3 minus 3 times the cosine of pi. Cosine of pi is negative 1, so that's 3 minus 3 times a negative 1. That gives me 6. Okay, and then f of pi halves, that is 3 minus 3 times the cosine of pi halves. Cosine of pi halves is 0, so that just gives me 3. So when I come back over here, that means I'm going to get 6 minus 3 over, well, pi minus pi halves is just pi halves. And that's going to give me 3 over pi halves, which I'm pretty sure we could leave it like that, but we also know what to do. We keep change flip. 3 times 2 over pi gives me 6 over pi. And that is your average rate of change. So it's literally the exact same, it's slope, and you do it the exact same way you do slope. No biggie. All right, now let's look at this. Average rate of change. The figure shows the graph of the polar function, blah, blah, blah. There's our graph. On which of the following intervals is the average rate of change? I want the average rate of change to be 0. Well, the average rate of change is going to be 0 when the numerator is 0. So if I'm going to do f of b minus f of a over b minus a, and I want the numerator to be 0, that means I need f of b to equal f of a. So let me look at this. Here's pi fourths. Here I am at pi fourths, and my number is 3. 3 pi fourths, and my number is 3. Well, are we sure about all that? Because remember, we have a negative radius, so you have to be really, really careful about that kind of thing. So let's, instead of, remember, you're going to get yourself confused and mixed around on here, because these all look like these should be at 3, but watch what happens. Actually, I don't know that I graphed this one. I didn't graph this one. But some of these have a negative radius in them. So I still don't want to rely on that even though I have it. I'm going to sketch what I know I can sketch, which is the rectangular form. Now this does not have a vertical shift, so I can just do my 3 and my 3. And since this is 2, that means the period is equal to pi. And this is sine, so when I plot this, it's going to look like this. Okay, sorry, got interrupted. Let's see. Okay, so I'm going to start here. I'm going to end here because I know what sine looks like. And then this is not negative, so I'm going to go up 3, and I go down 3. And then my period is, oh, goodness gracious. The period is pi, right? And so let's see what happens here. I might need to plot more than that, though, since I've got some 5 pi fourths and 7 pi fourths. But let's look at what's happening here. Yeah, I think I might, because that is pi halves, or that's pi, which makes this pi halves, which makes this pi fourths, makes this 3 pi fourths. So now I want you to look at it, because when we looked over here and said, oh, well, look, this is 3 and this is 3. Kind of looks like those would be the same. But when you look over here at this, at pi fourths, we have a positive 3, and at 3 pi fourths, we have a negative 3. So that means here, when I go to pi fourths, I'm plotting this point. When I go to 3 pi fourths, I'm actually plotting this point. And that's what can get confusing about polar graphs. That's why we like to stick to the rectangular. So pi fourths and 3 pi fourths, they do not have the same value. I don't like A. What I want is for them to have the same y value, so when I do y minus y, it zeroes out. 3 pi fourths, oh, and then 5 pi fourths. So I do need to keep going. I might need to smush it a little bit. So stretch this out. And actually, maybe what I'll do so I don't confuse you, it's fine if you stretch yours out. Let me just draw it better from the beginning. And this is going to, because I have worked this out before I got up here, but this might happen to you too. You're like, oh, wait, I think I need more. That's fine. Go do more. Because if I'm going to go to 2 pi, I have to have 2 cycles of this. So I'm going to go up 1, 2, 3, and 1, 2, 3. All right. So I start here, and then let me go all the way to the end. Okay, that'll get me 2 cycles. So then I go up to 3, and down, and up, and down, and it's still not perfect and gorgeous, but that's okay. I know that 1 cycle, and let me go ahead and draw it in, but again, I don't necessarily have to. I can keep the little dots, but sometimes it just gets too much stuff on there. All right, so from 0 to pi, that's 1 cycle, which makes this pi halves, and you don't always have to label everything, but I'll label at least that much. Okay, so we already decided we didn't like A. Now, so if this is pi halves, this is pi fourths, this is 3 pi fourths. So it's here we're going 3 pi fourths to 5 pi fourths. 3 pi fourths to 5 pi fourths. Those, not the same. I don't like B. 3 pi fourths, which is right here, and 7 pi fourths, which is right here, they have the same y value. I think I like C. Let's look at D. Pi fourths and 7 pi fourths. They do not have the same y value. I don't like them. There's my answer. I mean, you could work out the slope 4 times, like we did on the last one, but I don't know that you want to do that either. Okay. Now this last one here. It says in the polar coordinate system, the graph of the polar function r equals f of theta is shown with a domain of all real values for theta, for 0 to 2 pi on the interval of theta. On this interval of theta, the graph has no holes, passes through each point exactly 1 time, and as theta increases, the graph passes through the labeled points A, B, C, and D. So it's telling you that they're going in order, basically. On which of the following intervals is the average rate of change the least? The average rate of change with respect to R, the least. Okay, so from A to B, so I go from A to B like this, then A and B have the same R value, because here, I start here at 0, because it says we start at A, so I go to 0, this is the angle, and then this would be, oh God, I'm at 0, oh good Lord in heaven, what is happening now? Okay, sorry, I'm here at 0, I get to pi halves, and then I get to pi. And so even though it looks like a -2, like on the y-axis, it is if I'm at pi, and my radius would be 2. So these 2 radius have the same value, and I have symmetry here, which means my average rate of change is 0. So this is 0. Maybe that ends up being the least. Let's see. All right, B to C. Because I know that I am going in order, that's important. That means I am plotting these points with a positive radius. It's not like I'm over here with an angle and getting a negative radius, all right? So my x is increasing, and x is positive, or the r value is positive, and r is increasing, okay? So the average rate of change is positive because r increased. So here it's positive. Let's see what else we can figure out. From C to D, look at these. Again, symmetry and same R values. So this is 0. And then my rate of change here from D to A, okay, from D to A, we are positive and decreasing our distances, which means our rate of change is negative because R decreased. And when I want to know which one is the least, that would be D. Okay? So if you cared enough to watch this and you got even a little bit out of this, you might have a chance of getting one of those one questions. But remember, this is not a big ticket item. This is maybe one multiple choice question, if that, and there wasn't one of these even on your mock exam. Doesn't mean it can't show up on the real thing. But I wouldn't spend hours and hours trying to understand this when there's way more stuff that is guaranteed to be on the test that you really, really need to know.